Hey guys, welcome out for Rise of the Real-Time Stack. I want to first of all welcome you guys to Founders Den. I'm one of the partners and co-founders here at Founders Den. Just quick public service announcement. It's a co-working space for experienced entrepreneurs and Clubhouse. You're in the Clubhouse right here. Just building a really cool community of entrepreneurs. We always need high quality referrals for high quality teams, so please send them our way. I don't know if any of my partners are here, Jason, Jonathan, and Michael, but you guys probably all know them a little bit. And also, I would here to introduce Mike, who will get us kicked off for the event. A couple things that I don't know if everyone knows about Mike. First, Mike and I met in freshman English class back in the day. And the other thing that people don't know is that Mike's actually a serial entrepreneur, having started two companies prior to Metamarkets. So that's something that I think a lot of people don't realize, and I think it's a pretty cool fact. So I'll give it to Mike to kick off the event. Thanks, guys.
All right, so we have a few quick introductions, but so we have introducers introducing others, and before I turn over to Feng Jin, and then we'll have this great panel. And by the way, if any of you guys want a coupon code for customink.com, that was my first startup. Find me after the break. Happy to give it to you. You know, I think I just wanted to tell a little bit of three reasons why I think it's great to be here with these technologists tonight. And I think it comes down to sort of kind of when you think about the first time you came out to Silicon Valley and what it felt like. When I first came out here almost 6 years ago, I remember launching an instance on the Amazon Web Services and having this feeling that, like, wow, something big is going on here, you know, launching a Hadoop cluster in the cloud. And now, you know, 7 years later, I think many of us feel that, you know, maybe Hadoop is not really the future anymore. In fact, maybe it's in some ways something that's just everywhere. It's the past. I think the future today belongs to streaming data technologies. And as we have this emergence of a global digital nervous system with these sensor technologies that all of us carry in our pockets or have in our cars, this Internet of Things is really requiring the kinds of stuff that Andy and Eric and Jun and Matei have been working on, and others, many of whom are in this room. And I guess, you know, the last thing I'll just say is, this is really what Silicon Valley is all about. You know, when I was living in Boston, it's one thing to read about what folks are doing on Hacker News and to follow TechCrunch. It's another thing to be here in the heart, in the epicenter of Silicon Valley in San Francisco, which is maybe the new epicenter. And I think it's just fantastic that we've got a place like Founders Den, Data Collective, obviously Metamarkets sponsoring this event. So just excited to be a part of it. I hope you guys will take some time to hang out afterwards. Without further ado, I want to bring up Feng Jin, who's going to talk a little bit about the motivation for why he brought this great group together and why we're excited to be here. So Feng Jin is an engineer at Metamarkets. So thanks, Feng Jin.
Thanks, Mike. Cool. So this is the last word from sponsors before we get to the main event. But basically, I initially pitched the idea of this event for a couple of reasons. One of the primary ones being, over the last few years at Metamarkets, we've actually spent a lot of time building out infrastructure that's highly catered to doing low latency data ingestion and low latency querying. So this idea of like real time, a world beyond Hadoop. And I think the world with Hadoop it's a very naive solution. It's the first solution that a lot of engineers think about when you think about building out a data analytics stack. You can have Hadoop entirely in your backend. And as you get a little bit more advanced, and this is actually part of the history at Metamarkets, we realized pretty early on that building out an entire stack from Hadoop wasn't really going to meet some of the latency requirements that we needed. So what we did, and I'm sure what many of you out there do as well, is we introduced this notion of like a query layer on top of Hadoop. And like the purpose of the query layer is really to be able to ask questions on top of data and get answers back really quickly. So through a lot of experimentation and through a lot of trial and error, we ended up building this thing called Druid. And I'm sure Eric later on will talk a lot more about what Druid is. But when we deployed Druid into production, it gave us really low latency queries, and we could have answers on top of results extremely fast. But Druid wasn't enough. When we introduced Druid, how we had to load data into it was basically we had to run these giant batch jobs in MapReduce and dump all that data into Druid. And there was this completely separate problem of data ingestion. And as our stack evolved, we started adding more and more pieces to deal with the data ingestion problem. So we introduced Kafka as an intermediate message bus, which I'm sure Jun will talk a lot more about later. We introduced Storm to be able to do ETL-style processing on top of streaming data. I think Andy will talk a lot more about Storm later. And we still have like a MapReduce framework in place that's doing batch processing. And there's Spark and there's Hadoop as popular options here. And Matei, I'm sure later on will talk a lot more about Spark. So we've seen this growth and this evolution of a stack, and this is the stack that we run in production at Metamarkets. And this stack has really come together because of the hard work of many engineers at Metamarkets, and also because of the hard work of many of the core committers to these projects who are here today. So with that, I'm not going to take up any more time, and I'm going to hand things off to Jordan and the panelists.
I'm Jordan Novet. I cover big data and cloud computing. Thanks at VentureBeat, and before that, before I went to VentureBeat, I was at GigaOM, and I basically am trying my best to understand the business use cases for these things. I was I was reading Hackers by Stephen Levy, which begins in 1958 in Cambridge, Massachusetts. And basically, it's talking about how people were building systems and systems for systems to do artificial intelligence. And it was a crazy community, and people started actually going out to Stanford instead of doing it at MIT. But it seemed like at MIT there was some desire to build things so that others could build. And I get excited about that. I'm not sure what it is that's nerdy about me that does that. But what I've realized at VentureBeat is it has to have a business value. It has to be delivering a result. And so I'll be talking a lot or asking a lot of questions about the use cases that go beyond, what you guys do at your own companies. So with that, maybe we can hand it off and go around and introduce, starting with Andy.
Okay, I could do this. Yeah. My name is Andy Feng. I'm a chief architect at the Yahoo Hadoop team. But here today, I'm going to give an overview of the Storm. That was one of the areas I have been very passionate about it, and have been, we will talk a little more.
Hello, I'm Eric Cheddar. I created Druid. I wrote the first lines of Druid code anyway at Metamarkets a couple years back. Feng Jin has helped a lot on making that a reality, though. I'm here to talk about Druid.
My name is Jun Rao. I'm a software engineer at LinkedIn. And since I joined LinkedIn maybe just a little bit less than 4 years ago, I've been mostly working on Kafka. And we have seen Kafka from nothing in the code all the way to now a really popular Apache project, and it's been heavily used at LinkedIn.
Hi, I'm Matei Zaharia. I started the Apache Spark project as a research project at UC Berkeley. I was a grad student there. And now I'm actually full-time at a company, Databricks, that's commercializing Spark. Yeah.
Okay, I think I'm going to start to talk about Storm. So, yeah, for the folks who do not know about Storm, I think the one-line statement was Storm is the Hadoop for real time. Right? So it is designed to be a platform enable you to do your real-time processing, writing your business logic, and the Storm as a platform going to handle all those heavy lifting for you. The Storm as I think it has actually it's a very new technology. It has only been in the market, I would say, less than 3 years. It was originally developed by Nathan Mars and his friend at the Backtype, which was acquired by the Twitter in 2011. And then they decided to made it open source available on the Git. Then at that point, I think it was about 2 years back, and it said we at Yahoo we heard about this Storm. We started to play with it. Then we said, this is a cool piece of technology. We really enjoy reading the code. Then we started to do the collaboration with Nathan. And part of that collaboration was make Storm as an Apache open source project. So I think that luckily last year, September last year, now Storm is an incubation project at the Apache. Oh. Okay. Okay, so at this point, I think at this point, Storm is a very active project and has a huge number of the size of user communities, the development community is quite huge. And one thing I was happy to, one day I was visiting Nathan Mars's website, one day I saw 12,000 people was reading his code. What else, what kind of piece of the code people there, 12,000 people was keep reading it, right? That's kind of amazing. So then just to give you the flavor of the user community, here's I was just pick some of the sample, the companies that are adopting Storm as a key platform for them. And certainly you will see all the familiar name over there, right? So let me just give you some example of what we do at Yahoo. I guess this is the slide that said how big we are at Yahoo for Storm. I guess that's why we are, at this point, we are invested a good number of our engineering resource, make it really solid. Right? So currently we have, logically, I just even could not remember who are my customers at Yahoo anymore, right? You see, there are the people we try to use Storm to improve the monetization stuff. We use Storm try to improve the user experience. And in the bottom, like this thing, we even try to use Storm to make sure our system reliably running over there. And one of the things I want to just make sure be clear here is at Yahoo at least, Storm is just a part of our solution, right? Hadoop continue to be all the key technology for our things. So if you see the thing over there, logically we have the batch processing technology such as Hadoop and Spark and coexist with Storm and to do our job. So just from conceptually, Storm is have a very simple concept. Logically, it's designed to process the streaming of events. The events we call the tuple, right? And then in the tuple, you could all the stuff in it. And what we ask people to do is define your application as a DAG of the processing unit. We have two types of the processing unit. One we call the sport, one is called board. So you could see the thing there, like the spot with this thing, like starting the tuple, the streaming things, and both is the thing, take this tuple, do something about it, and then emit something for the downstream to do their work. And just like the Hadoop, Storm is designed to do to run in a distributed environment, to taking care of the things, the parallelization for you. So you could, write your logic decks, and you could say, what level of the parallelization you want. And then we give you all the technology to how connect those things together. And then one of the key things that we try to do is try to give you some guarantee about the reliable processing, right? So under the cover, if you're thinking about some events coming into your tuple, at that thing, going to go to some board, and from there going to generate additional new stuff. So conceptually, it's create a tuple tree in it. So because we are dealing with this distributed environment, so some of this thing going fail, right? So as a result, we offer the variety of the guarantees for you. There's the best effort. You could be, if you really do not care the reliability, or you could give you at least one guarantee on it. Or even better, if you really want, we could give you the exact once guarantee for the reliability. And then so there are several layers of the abstraction we give to you. The Storm API layer is very basic. So just almost, if you think about it, just like MapReduce kind of thing, right? Then on top of that, there is also the high-level abstraction we offer. One of them we offer is this thing called a Trident. Trident, if you're thinking about the operation over there, that's like a cascading type logic operation given to you. What it's doing implementation logically is say, instead in the Storm layer, we try to do every tuple, we do the job. In the Trident layer, we basically do say, let's do a mini batch, and from the mini batch, we do the better job for you. And then let's talk about the underlying system things. So very simple thing, right? So you have this Nimbus is all the master of all cluster, right? Just like the job checker in the Hadoop. And then the supervisors, those are logically those are machines that we're going to run your application logic. So when you have your topology over there, we're going to launch your code inside a new process called workers. Inside the worker, we're going to launch all the tasks for you. And then those tasks will run as a daemon process over there. They just keep processing the things. So that's one of the main difference here, if you think about it. So in the batch, in the Hadoop land, like for every job you needed to do, it need to launch as new processes. In the Storm, it's all the daemon just sitting there, do the job for you. And let me just quickly hand over. I think one thing I wanted to make sure be clear is the Storm is designed to be a good team member in this big data platform. So just like I mentioned earlier on, like in Yahoo, for example, we have the Storm, we have Hadoop, we have Spark. All of them are coexist in a beautiful cluster. I think that's what I'm going to do. I think there's a lot of additional information one could dig into it. That's, I think, the quick overview of Storm.
Apparently,
more Storm code. I've not intended to show.
So everyone understood all those slides I just jumped over, right? I just saw it and got it. Okay. And you got the introduction already, so I'm going to skip that. I'm going to talk to you today about Druid. I never know what to make my titles, and so I just put random words up there that I thought were good. So it's immediate slice and dice aggregation engine. I'm going to jump into the requirements of the system real quick, but just at a high level, I'm going to try and give you a high level overview of what Druid does, throw throw out some ideas of what it is. Technical details, all that sort of stuff, you're going to have to check up afterwards to look it up. There's a little bit too much to actually go over in 10 minutes. But Druid is a query system. Think MySQL, think Vertica, think all of those, but don't implement joins and get rid of SQL. And that's kind of what Druid is. The requirements for when we built it was we wanted brides to be able to eat cake. Actually, this is data ingestion. We wanted to be able to ingest data quickly and fast and a lot, as quickly as possible. We also wanted to be able to cut pumpkins or slice and dice the data. So we wanted our queries to be able to run. We wanted to be able to filter the data by any dimension combinations that we wanted and not limit our users in which dimensions they look at. If you're familiar with BI technologies, a lot of times you have to choose which filter combinations people can and can't use. We didn't want that. And lastly, we wanted it to be available. And that should speak for itself. But yeah, so in words instead of pictures, once again, there's ingestion. We wanted it to be real time. As soon as the data hits the system, we wanted it to be queryable. You should be able to get answers immediately if you want them. You should also be able to get answers about the past if you want those in the same system. We wanted to be able to slice and dice, basically do arbitrary Boolean filters. If you want to do an OR clause with 500,000 things in it, you do an OR clause with 500,000 things in it. That's not a very common use case, but you can technically do it. And then we want it to be available. We didn't want downtime. Downtime is evil. We built it at Metamarkets. Metamarkets is a software as a service company that provides analytics to advertisers, real-time bidding marketplaces, and stuff like that. As a software as a service company, you kind of need a product that's always there because you have no clue when your customers are going to be looking at it. And so we were unable to tolerate downtime. A lot of back-end systems and a lot of analytics systems, they say, well, our analysts, they go home at 5 p.m., so whatever, we can take it down overnight. It'll be up in the morning. No one will know the difference. We said, no, it's unacceptable. We can't have that. So those are the requirements, and you can just trust me that we did it. The question is how. This is the original whiteboard diagram. This is the Druid. And then down in the bottom left there, everyone calls it a pig. It's not a pig, it's Winnie the Pooh. I probably can't say that. They're probably going to get mad at me, but whatever. It's Winnie the Pooh, that's why he has a pot of honey. Seriously, the architecture follows from the Power Rangers. It's what I have called a sum of parts architecture. I'm sure someone else has used the word before, but the Power Rangers, kind of the way they work is each Power Ranger can turn into a Zord. And that Zord is more powerful than the Power Ranger and gets to do things. Is interesting. Anyway, he does things and he fights stuff. I think when I do this, noise happens. Anyway, okay, I'll move it over here. Okay. All right, Power Rangers. The thing is, the individual Zords aren't strong enough to actually defeat the monster in the end of the episode. What they have to do is combine together into the Megazord and take on that monster. Druid follows a similar architecture. We have a bunch of different individual node types that do one thing well. We have real-time nodes that sit on a real-time stream, ingest the data, buffer it, and process it, and then hand off to historical nodes. Historical nodes hold historical data. They process queries on that data without worrying about reading in the stream. We have broker nodes, similar to a search architecture, that routes requests for you and other stuff like that. For more details on that, there are other talks online. There's documentation and other things like that. But the idea is that there's a bunch of different nodes that do one thing well, and when you combine them together, they form a system that is useful and beneficial. Where does Druid fit in the architecture of everything? The answer to that is that it fits on the right side of the screen, where the left side of the screen is blue squares, which are streams of data, and they're coming in, and we use Kafka initially to hit the data. Kafka is great infrastructure. Jun will tell you all about it, but it's great infrastructure for pulling in data and holding it and allowing you to process it It's good at handling the fluxes of the internet and allowing you to process it afterwards. Man, that noise, it just keeps happening. Anyway, with Druid, you can ingest data directly as a consumer on top of Kafka. You can also, and Feng Jin mentioned this at Metamarkets, you can use Storm to do an initial processing. You can use Storm essentially as a CEP engine, a complex event processing engine, to do some processing business logic, merge streams and stuff like that, and then push that merge stream into Druid. You can also use Spark, put your data into Spark, and for data that you want to expose to customers, for data that you know you want to query on regularly, that you need concurrent access to, and with heavy slicing and dicing, you can load that data into Druid, expose that to your customers, and still have your warehouse in Spark or Hadoop or whatever you choose to do. And so that's generally where it fits. Generally, this side of the equation, if you were using Storm or something already, you would put it in MySQL, you would put it in Cassandra, you would put it in something like that. It's another option in that group of things. Now for buzzword soup. I'm going to tell you a bunch of buzzwords about what we do, and you're going to be like, wow, I've heard those words. That must be an awesome project. It's column-oriented. You only have to scan what you need. This allows for faster scans. It also allows for other benefits. It's distributed, meaning that the queries are parallelized. If you want more processing power, add more nodes, you have more processing power. If you also get redundancy and fault tolerance through that because you can do replication across the nodes. It's real-time, meaning when the data is ingested on the real-time nodes, it's immediately queryable on the real-time node. You can see that immediately. You have to do the query, but it is immediate. More buzzwords. What are these? These are bitmap indexes. So we use bitmap indexes in order to implement the filtering logic. We pre-index all of the dimensions of the data and then combine them in order to figure out what rows match, and then we run your queries on top of that. We compress data. We use a dictionary encoding, LZF encoding. These are all things, if you're interested, the internet has tons of information about them. It's fault tolerant, as I mentioned before. We use hot replication, meaning that data can exist on multiple nodes at the same time. If it does, then queries will use all of the nodes that have the data, so you can avoid hotspots by increasing your replication. And it will also do balancing, or attempt to do balancing. This logic could be better, but there is logic there to try to balance stuff. Another set of buzzwords, there's approximation algorithms. We have hyperlog implemented in Druid. This allows you to approximate cardinalities. So you can do unique queries. You can do basically count distinct in a distributed manner as long as you're willing to accept a, say, 2% error rate. There's approximate top ends implemented. There's also caching. There's what I call a perfect cache invalidation strategy. It's generally a really good cache invalidation strategy, but the word perfect sounds better than really good. So yeah, no, it's good. It's on a per segment basis. That will make sense if you actually learn about Druid. Otherwise, just know it can do caching, and caching is cool. There's also rolling deployments. This gets into the availability thing. Downtime is evil. At Metamarkets for the last 2.5 years, we have not taken downtime for deploying code in this system. So we have constantly deployed new software. There are weeks where we will deploy 3, 4 new versions, no downtime. Yeah, that's something I'm pretty proud of. Lastly, some cluster size examples. One example cluster represents over 3 trillion events in 110 billion rows worth of data. It's across 80 nodes and maintains a 90th percentile query latency under 1 second and a 95th percentile query latency under 2 seconds. I believe those are respectable numbers. Another example cluster is a real-time cluster that ingests 150,000 messages per second at peak. Over the course of a day, it's ingesting 7 billion events per day in real time, queryable immediately, and yeah, so hopefully those are impressive numbers. Otherwise, well, we need better ones. Lastly, Druid is open. As you probably know, given that this panel is about open source stuff, you can find out about us at druid.io. It is also, the code is on GitHub under metamx/druid. Metamx stands for Metamarkets. We have a development list on Google Groups, and we also sit in a channel, druid-dev on IRC, on Freenode. And that does it for my talk, which means I'm handing it over to Jun.
Thanks. So before I start, I just want to do a quick show of hands. How many people here heard about Kafka? Pretty much everybody. So how many people are using Kafka in production? Maybe about half, or maybe a third. OK. So let me just start by describing a little bit of problems that we want to solve at LinkedIn. Go right. Go right? Yes. All right. OK. So LinkedIn is one of those typical internet companies. The value of LinkedIn is in its data. The more data we can get, the more insights we can dig out through analysis of this data, which in turn allows us to build more informative product, which allows us to give those insights back to the user, which drives us more traffic. So some of those data are probably what you would think. Those are the data stored in the traditional databases. This includes things like, in LinkedIn's data, the profile data, and all the information about your connections. But that's actually only a small percentage of the data we have. There's a lot more of those data, what we call those interactive or log data. So some of those interactive data are generated by human beings. If you go to LinkedIn's homepage, if you click on a link, if you post an update, or you just type in some keywords, all those are very useful information for us. Some other interactive data are actually generated by machines. So for example, each service at LinkedIn generates service metrics, service logs, service calls. Each machine is generating various metrics about the healthiness of the machine itself, CPU load, I/O load, network traffic. So all those data in terms of value, actually, they are almost as important as those more traditional database data, like profile connection. So together, they allow us to generate more insights and build better products. If you look back maybe 10 years ago, a lot of those interactive data, most places you can't afford to store those. Just because the size volume, it's easily 2 to 3 orders magnitude bigger than the data you store in the traditional database. But these days, you can actually afford to do this. A lot of that has to do with some of the new emerging technology, especially Hadoop. So LinkedIn adopted Hadoop probably around 5 or 6 years ago. Around that time, what happened is an engineer will think about how to make use of a particular type of data. And it was, if I can get this data in Hadoop, then I can build this better product. So we'll add a particular pipeline to get this data into Hadoop. Then 2 weeks later, someone else will think about the same thing. Maybe he needs like another set of data. Then they will build another pipe to get data into Hadoop. This is actually when the problem starts. The problem is, first of all, this type of data is actually unbounded. You know, every few weeks or every minutes, there could be a new source of data, interesting data that's available. And you somehow need to integrate that into a system. The second problem is, over time, we realized Hadoop is actually not the only platform or system that needs this data. It's a pretty good starting point. But then, for those data that's in Hadoop, your search engine, especially your real-time search engine, may need it. Then, next week, maybe a monitoring system needs it. Then your email system, what about a recommendation engine? What about security system? So on and so forth. So this phenomenon of adding those sort of separate pipelines over time gives you this problem, which is you end up having on the top all those data sources that has interesting data, and you have bottom all those services that need to consume those data, but they each end up having to know each other. So this quickly becomes an unmanageable and untractable problem. Each pipeline has probably some redundant work. There's a lot of room for mistakes, and there's no way you can monitor this. So that's the problem we started to solve maybe 4 years ago. So what we want to do is to turn this picture into something like this. So we'll introduce a centralized data pipe layer. which sort of decouples those services that have data from those services that actually wants data. So if you have a service that you think you have some interesting data, all you have to worry about is to build a simple adapter so that you can publish your data to this central data pipe. If you're a consumer, again, you don't have to know anything about those producers. All you have to do is to be able to tap into this centralized data pipe. So that becomes a much more cleaner architecture. It's more scalable, and we can potentially monitor the centralized data pipe better. We can give enough capacity. We can tune its performance for throughput. A lot of good things can happen with this better architecture. Then the question is, what should we use to build this centralized data pipe, which is the key part of this? And if you look back, you think, yeah, this is actually like a messaging system, right? All those services at the top are essentially publishers, and all those systems at the bottom are essentially subscribers. So what about we just use like a messaging system? So that's what we started probably 4 years ago. We tried a few off-the-shelf messaging systems, one of which is actually ActiveMQ. Just long story short, I think it didn't go very well. There are a couple of fundamental reasons. This is not just to pick up, to do any picking on ActiveMQ. But one of the fundamental reasons is those traditional messaging systems are not really designed for this volume of data. Remember earlier I said this kind of interactive data is easily 2 to 3 orders of magnitude bigger than data in your traditional databases. A lot of the earlier messaging systems are designed to work with data in your databases. But they're not designed for handling data that's 10 times, 100 times, or 1,000 times bigger. So a lot of systems, they don't have like a truly scale-out system. The throughput is not great. Another problem is actually on the consumer side. As you can see from those consumers, I think in the bottom, right? It actually varies from one extreme to another. In one extreme, you will have Hadoop, you will have your data warehouse. Those are more sort of batch-oriented offline consumers. So, they can be down for a day for maintenance, and then they want to resume consumption afterwards. But on the other hand, you will have lots of real-time monitoring, real-time indexing, real-time security analysis. These are pretty real-time. They want to be able to keep up as soon as those data come in. A lot of traditional messaging systems, they're pretty good at handling those real-time systems. This is what those messaging systems is really about. But they are not really designed for handling those consumers that can be lagging. Often you will see the performance of those systems start to drop significantly if you have consumers that's lagging even for hours because they can't buffer a lot of stuff in memory. So that's when we start building our new solution. That's actually when we started building Kafka. So in short, Kafka is sort of a new generation of messaging system. At a very high level, it has this traditional messaging architecture. In the middle, we have this broker tier where we store and serve those data as messages. On the left-hand side, we have those producers, which can talk to those brokers. And on the right-hand side, we have those consumers who can subscribe to those systems. And one of the unique things with Kafka is actually a multi-subscription system, which means a single message can be subscribed multiple times by different consumers. So it's not just one-to-one, point-to-point delivery. You can actually publish once and subscribe multiple times, which is actually a pretty useful feature for a lot of our use cases. Then, in terms of technology, that's how we differ from some of the traditional messaging systems. The first thing we did is we want the system to be high throughput. So we have a very simple and specialized storage layer that allows us to store those data, especially high volume data, efficiently. It also allows us to handle those mixed use cases where some of the consumers can be consuming really old data, some of the consumers are consuming more real-time data together in the same platform. We have built-in batch API that allows us to sort of amortize the RPC cost. We have things like zero copy transfer that allows us to efficiently transfer data from the broker tier all the way to our consumers. The second thing we added is we just have to scale out. So we build Kafka from ground up as a distributed system. We leverage some of the state-of-the-art system like Zookeeper around that time, allows us to build a pretty sophisticated cluster management system so that we can add new hosts into our cluster if we want to grow our capacity or grow our throughput. We also allow parallel producing to our system, as well as some coordinated consumption of data. So this is one of the interesting things with Kafka is you can simultaneously start multiple consumers within a concept what we call group that allows us to distribute the data in a particular queue or topic into those consumers sort of more or less evenly. That allows for parallelism. Last but not least is on fault tolerance. So over time, what we are seeing is people are putting more and more important data into our system. It's not necessarily just log data that you can throw away. People are putting more traditional queuing data into it. People are putting in some of the more user directly generated data into it. And even for some of the like human-generated tracking data, for various reasons like reporting, coverage, you need to have those redundancy. So over the last year and a half, what we built is a built-in replication feature in the cluster, which allows us to publish a message, each message, so redundantly on multiple brokers. That allows us to have higher durability as well as availability. So any of the brokers in our cluster can go down. We can still serve the data as if nothing has happened. Same thing, we build some fault tolerance in our client layer. For example, in the consumer case, if you have multiple consumers in the same group that jointly consumes a topic, if any of them goes down, we'll automatically detect that and redistribute the data to the surviving consumers. So these are sort of the distinguishing factors we have with more traditional messaging systems. Even though all the stuff I just described is we're trying to solve the problem at LinkedIn, but over time we realized that this is actually not a problem just unique to LinkedIn. A lot of companies, as long as they have data or they have a sizable website, they will have similar problems. So that's what we see the value of just open sourcing it, because we can probably collaborate with the open source community better, and we'd be happy actually to share some of the technologies we have with other people. So far, I think other than LinkedIn, we have a lot of the Web 2.0 companies are using that. Even some of the more traditional enterprise companies are starting to use Kafka as well. So with that, I think I'll give it to Matei.
Okay, thanks. So I'm going to talk about Apache Spark. So Spark, so actually the word real-time is fairly overloaded. There are a lot of real-time data systems out there, and there are at least two types of systems people consider for real-time. One is fast ingest, essentially, from the time data comes in to the time you have a result. And this is what systems like Storm and Kafka enabled. The other way people use real-time is even if you have completely static data, being able to ask a query and get an answer back quickly enough so you can interact with it in real time. So Spark does both of them. So actually, I'm going to talk a little bit about how it does both. So what is Spark? So Spark is a fast and general computing engine that's compatible with Apache Hadoop. It can run in Hadoop clusters using Yarn, and it uses the same APIs as Hadoop to access data, the input format API. So anything you can run a MapReduce job on, you can run Spark on. You can read that data and run this kind of job. But Spark generalizes the MapReduce model to let it do more things. So the way to think about it is, to do a superset of MapReduce. And we've actually managed to generalize it to the point where a lot of things that usually you may use separate systems for can be done with Spark. And in particular, it improves two aspects of MapReduce. First one is efficiency. So Spark supports general graphs of computations, not just the map and reduce phase of MapReduce, which makes it more efficient when you have more complex computations that need to do more than one grouping operation. The second way it extends it is with support for in-memory storage for keeping data sets around on the cluster between parallel computations, which helps in a lot of applications such as real-time queries or anything where you go over the data multiple times. And together, these things let it run as much as 100 times faster than just plain MapReduce for the in-memory data, and sometimes even up to 10 times faster on disk for the more complex computations you're running there. The second thing we improve on is usability. So there we have these language integrated, very concise functional APIs in Java, Scala, and Python that make it much faster to write jobs. And we have the interactive shell. You can use it from the Scala or Python shell. And these can mean 2 to 5 times less code. So finally, on top of the core engine, Spark is also this growing general stack of systems built on top. And all these systems, because they build on the core engine, they can all interoperate with each other. You can actually combine these systems into one application. So some of the systems on top include Shark for SQL. Shark is a port of Hive to run on the Spark engine. Spark Streaming, which is real-time in the sense of data ingest and you get answers from it immediately. GraphX, which is a graph processing system we recently put out, and MLlib for machine learning. So these are some of the libraries we're building on top to give you higher level abstractions for working with data. So I'm gonna, instead of talking into a ton of details about Spark architectures and details, I want to tell you sort of the big picture of where we see it fit and why we think it's exciting to approach data this way. So essentially what happened in big data systems is that we started with MapReduce, which enabled people to process data at a larger scale than before. And a lot of people started collecting data for that purpose and passing it through MapReduce. And MapReduce was a very general engine. If you remember the initial stuff about it, Google pitched it as, oh, look, this is super general. But it turned out that as you got more and more complex or demanding use cases, it wasn't enough. So instead, we got this profusion of specialized systems that tackle usually very specific point workloads, like say just interactive SQL queries, or just stream processing, or just machine learning. And now you have this zoo of systems that you need to learn. What Spark did differently from these systems is that it generalized the MapReduce model in a way that actually allows it to support all of these workloads in the same engine. And this has some very powerful benefits when you get to complex applications that combine them, and also in terms of operations. Only one engine to operate, one engine to learn, one engine to monitor, and so on. So there were two things that we added to it, the general task graphs and the in-memory data sharing. And together, these turned out to be enough to capture these previous models, or at least to match the performance and properties of the previous system. And this has some really nice benefits for both the engine and for users. So for the engine, when you look at Spark, comparing it with other engines in this space, you'll see that you can do a lot with very little code. And that means that we reuse our effort. Every time we improve the core engine, all the systems built on top of it improve as well. This graph here is just a very quick comparison. It's comparing Hadoop MapReduce, Storm, Impala for SQL, and Giraffe for graph processing with Spark. Now, Spark is roughly the same size as these things. It's written in Scala, so it's expected that it will be a bit smaller. But it's in the same ballpark. We didn't gain too much complexity from the generality. But the really cool part is when you start comparing it with the specialized system. So when I compared with Storm, I was cheating. I compared the core Spark engine against Storm. But if you look at it, Storm does a lot of the same things that a MapReduce system would do. It has to do parallel distribution, fault tolerance, aggregation, all that stuff. When we built Spark Streaming on top of Spark, it's just a library that uses the same underlying engine. So we were able to do this in a fraction of the code. When you look at SQL, engines like Impala, there are a lot of these out there today, are a brand new engine that is, again, replicating much of the details, much of the hard parts of MapReduce, just to do this one workload. We instead took Hive and changed the back end of it to run on Spark, and we can achieve excellent performance with just this one thing. And finally, same thing is true for graph processing. So engines like Giraffe is a new engine to do Pregel, and we can do this on top of Spark. So this has really powerful benefits for us, the developers, and for the users who only have to operate and manage this one thing. Now, by doing this, you might ask if we're losing any performance. But actually, in comparisons with these previous systems, Spark does quite well. So this is just one comparison with Storm. This is actually Storm 0.8. So maybe it's slightly different. But the cool thing here is we're in the same ballpark, but we're running this on a MapReduce engine. And actually, Spark offers exactly one semantics by default here, whereas this was Storm with no fault tolerance enabled. So actually, we get some interesting benefits from this common model. This one here is comparing against SQL. Lots of people have tried to speed up SQL. We do just as well, basically as most of the other systems we've seen. And again, we do it in a fault-tolerant way because we're built on Spark. And then this one here is for graph processing. And again, we gain similar kind of speed up. For users, what's really cool about this is that you get a unified programming model. So is this cutting out? Or? Oh, I see. OK. All right. Okay, let's hope there's not some crazy feedback here. OK, so yeah, so for users, what this means is that you get a very powerful programming model where you can combine these types of systems. So here's some code you can write in Spark that's pretty difficult to write in any other data processing system today. We start by doing a Hive query. So this is the Shark API that you can call from Scala, where we pass in a SQL query, and we get back the result as a distributed collection of pairs of doubles. So we pull out some data points, like say tweet locations. Then we run k-means on it. I'm calling the MLlib implementation of k-means, so we train a k-means model. And finally, at the bottom, we're calling Spark Streaming. Spark Streaming, we start reading tweets from Twitter. We pass a map function on them to do some transformation, and then we do reduce by window to count the tweets that fall into a specific cluster. So this kind of application that combines these types of processing becomes very easy to build, and many real workflows need to do this. So what it means for users, another aspect apart from programming is also saving time. When you run separate systems, you have to write the data out to some storage system like HDFS and read it back between each one. And for most data computations, the I/O of doing this is way more expensive than the actual computation. When you run Spark, you can do these on the same in-memory data. So these workflows end up running faster. And of course, you can use it interactively or or just write to HDFS. And finally, just last thing I want to end up on is the community. So Spark is a fairly new project. It was first open sourced in 2010, but we've been very fortunate to have a very excited and fast-growing open source community. So in a few short years, we've actually become one of the most active developer communities in big data. And as of last count, over 140 developers have contributed to Spark from over 30 companies. Actually, another cool fact, recently I was doing some numbers to check number of contributors to each project in the past 12 months. And recently Spark has surpassed Hadoop MapReduce and every other distributed processing engine in open source in terms of contributors in the past year. So that's a very exciting time for us. So that's all I wanted to say. Happy to pass it on to the rest of the panel.
I think when I listen to all these projects and the stories of origin, I wonder what went on behind the scenes. For example, at Metamarkets, I wonder how much pushback, I wonder how much discussion there was among engineers to do that. And if there are perspectives from the others, I'd like to hear them. So Cheddar, maybe you can talk us through that process of how it got to the point where it was ready to be shared with the rest of the world.
So the question is the opening up of the software? Yeah, there's been lots of discussion about it. The big fear, especially for Metamarkets, which is still a young startup that is trying to do things, there's always a fear of cannibalism. If you open up your infrastructure, are you destroying your company? Because now people can take your infrastructure and do exactly what you do on top of it. There are also, there's questions also. This, I think we learned more after we opened, but around resource allocation. after you open it up, there's a certain amount of effort that you have to put into grooming and maintaining the community and keeping things going, and that effort might not be exactly what the company wants to be done on the project at that point in time. And so like there are definite concerns. I think on the flip side, like something that Jun mentioned when he was talking about Kafka is through the contribution you get other people looking, you get other people contributing, you get them using it for their use cases, you get more product roadmap input kind of from how other people are using it. And I think in a larger organization, you can often kind of get stuck in a rat hole around, well, where are we taking this project? And if you open it up, then you can get more input into a broader spectrum of areas. For Metamarkets also, I mean, it's probably something you're not supposed to say because it's but recruiting. It's a great recruiting tool. Opening up your technology, engineers like working on open source stuff, and giving that, it makes engineers happier and other things like that. And so I think the other thing is we also kind of figured that, you know, this stuff is going to be commoditized anyway. If that happens, and if something else, some other infrastructure comes around, we're going to have to switch to it. And so if that's going to be the eventuality, then let's try and put our stuff out there and build a community around that rather than allow someone else to build up a community and pull the rug out from under us kind of stuff. I mean, it's, of course, all of that stuff, you only know if it was a good decision or not afterwards. And yeah, anyway.
Yeah, so I'll just add a little bit to my experience at LinkedIn. So in terms of culture, I think the culture at LinkedIn in terms of infrastructure is LinkedIn's value, as I said earlier, is in its data. So LinkedIn is not going to make money just on its pure infrastructure. It does need good infrastructure support its website, but it's not going to like sell its infrastructure like other technology companies to make money off it. So from that perspective, it's pretty open about sharing its technologies with outside. So we can sort of talk about it. We can go to conferences like this. We can open source it if we want to. Overall, it's sort of a win-win situation because from engineers' perspective, there's nothing better than engineering seeing its code being used by a bigger community. Not just in one enterprise, but potentially in many other places. From LinkedIn's perspective, it does mean that some of the LinkedIn engineers has to put it a little bit more time, especially if you open source a project to support potentially some users outside LinkedIn. But what LinkedIn got is a lot of branding. In terms of hiring new engineers, there's nothing better than being able to tell those engineers what we have been working on, what are technologies we've been using, and potentially experience those technologies before they even join. And as a secondary, I think it probably also gets some external contributions, as like Eric said, especially in terms of documentation, finding bugs, and just improve the usabilities.
I will add something in a slightly different angle. So, when 2 years back, when I was looking into the storm things, at that point, Yahoo had a very interesting debate. Because at that point, I think even still today, some of you know, there's some open source code Yahoo contributed in the Apache project. So that was the S4, right? So the question at that point was say, you know, there was some piece of the code we contributed, and there's a good piece, you know, then why are you going to jump in this piece of this open source developed by some other company, Twitter, at that point? So, you know, why you jump in it? Yeah, some of the discussion was about the technical strengths, about those alternative choices you're going to make. So I think the very two important thing, in addition to that, was the community you have. right? So then we kind of look into the, how big is the momentum you have for the community you have, right? You could have a piece of this thing, nobody care or something, right? So for the Storm was a very strong community, right? And then from the looking into the, then the other thing we really paid attention to was the license agreement you have for those open source. So for us, at that point, Nathan has I don't know what's it called, the Apache-like or was the kind of license that he had put on there. So while some of the discussion we had was saying, we really do not like that license deal. We prefer Apache license, open source license. So if you guys may notice, there was several, during that period, Nathan quietly replaced his license to the Apache license. So some of those things, I think when you select those technology, I think, there's other different angles. I think at this point, you're thinking about, as the Storm as a project and now is the Apache project. At this point, Nathan not really spending too much time on the Storm, but the remaining community would push very strong. As I mentioned in my slides, we are about to release our first release from Apache, from the Apache Storm.
I've been told we have 15 minutes, is that right? Okay, it's a very short time for me. I mean, I have lots of questions I could ask. Oh, but I actually wanted to ask you, Matei, with Databricks, how do you actually move into the stage of building a company based on that technology? I see multiple open source technologies being commercialized now. One of the most exciting ones is Docker, I would say. Also, the RethinkDB is very interesting as well. I wonder what challenges you experience in doing that.
Yeah, okay, so to answer that question, so with Spark, I think we have a very unique advantage in that the technology has already existed for 4 years, and people, certainly the early adopters, web companies, had started using it before, but numerous other people had looked into it, had prototyped things, and wanted to get commercial services and help around it. So we had that advantage that's harder to do if you start with a brand new project. So in a sense, we already knew that it was something useful that people would look at. The other thing that we're benefiting from is just the commercialization and success of Hadoop in the enterprise. So essentially what happened is early on, the first companies that pioneered Hadoop explained it to enterprises and even to more traditional technology companies and explained to them this new way of processing data on commodity clusters. Now they've already installed Hadoop, they already have all the data, and we provide something that fits right in and lets you do better processing. So it's a much easier sell in that sense. And you can see, so like one of the things we've announced is Databricks has partnered with Cloudera to provide Spark and CDH. It's actually available now. And it's great that that install base already exists. Cloudera is very well aligned with us because they want their customers to be successful, and we are able to sort of ride this wave of Hadoop. I don't think it'll be the same for everyone.
This is an interesting question. Someone suggested that I ask. Will there ever be a generic stack that is good for all event data? And so especially toward real-time analytics, what would it be composed of if such a thing ever could exist that's very standard?
Yeah, I think it's definitely promising. So if you look at the success of Hadoop, right, it has HDFS, which is a storage system, and it has MapReduce, which is the computation engine. It sort of opens up a new world where you can just pump in any type of data, infinite amount of data into it, and it can do analysis on it and use sort of any customized code, logic to do an analysis, and do it in parallel. So these are the things that are either impossible to do or expensive to do before, but now it's cheaper. But so a lot of, I think today, a lot of traditional enterprises, right, starting to embrace this kind of stuff. That's sort of I would say maybe the first phase. So once people know they can get value out of this data, if you say you can get value quicker, I think everybody would want it. So I think that's what I see the promise of this new real-time platform. So similar to Hadoop, I think you will need some equivalent of storage system that is not batch-oriented, but allows you to deliver those data in real time with high availability and durability. And you need the equivalent of platform on this real-time feeds of the data that potentially can plug in arbitrary logic, potentially handles a lot of parallelism, handles a lot of fault tolerance for those people. I think it's still pretty early, so we are sort of in the very, maybe some of the early stage of this. I think there are a lot of early adopters, but the market is still early. It's probably just going to take time. I don't know when that time would come, but I definitely hope for it's promising.
I'm going to take the chance to be contrarian a little bit and maybe spice this up. But sorry, I think if we look at the question of will there ever be a generic stack for event-based processing, I think if we go back and roll the dial back 20 years, someone might have been asking this exact same question about relational databases. And at that point in time, relational databases, sure, they're going to solve all problems. But I think that as we move forward and solve a problem, we will find newer and more interesting use cases and problems to solve that will mean that all of the generic stuff that we built no longer works, and we're going to have no event processing streaming real time or whatever to show up and have everyone take over. But yeah.
Yeah, I'll add to that a little bit since we're talking about databases as well. So I think in a lot of markets or types of software, as the market matures, you do get convergence. So actually, the relational database is an interesting idea, right? If you think that 20 years ago, or even 10 years ago, we thought about doing all data processing in it. Well, the reason for that is that before SQL existed, there were actually many different models, different systems that would manage data, let you link it up in different ways, object-oriented databases, all that kind of stuff. And actually, the market did converge on one, and having a standard there was useful. And the standard was good enough for the applications at the time. So I think this is the same thing that may happen here if this stuff becomes very commonplace.
I guess I will add one thing in it. I think at this particular moment, if you look into the technology space for the interactive analytics, sounds like chaos, right? There's the Hive, there's the Shark, there's the Impala, the Druid, all those things. I think from the technology side, I think that's the thing we needed to do, putting them together. On the other hand, I would say it's the part of the job our user community should push, right? I think it's the time to push those players for the sake of the industry, try to bring all those things together.
Before I jump into more questions, I want to see who might have a question. I don't want it to be just a very closed environment, so I want to see if anyone has anything to ask. No. Oh, yes.
So for the Druid person, a lot of the index people that search, the field searches, let's say solar, kind of more like indexing of data and being able to slice and dice without joins, which is kind of what Druid does, have kind of similar aspects. And beyond even tokenization and other stuff you can, I guess if you're just looking at singular values, right? So I wonder what brought you to say, okay, no, I'm not going to look at regular converted index technology and build something on a different aspect.
Absolutely. So the question, for if you couldn't hear it, was that Druid's indexing technology and the way that it does slicing and dicing is very similar to search. why didn't you look into search, or why did you choose to move into why did you choose to implement something on your own? That's a fair rendition of the question. Yes. Okay. So interestingly, the beginnings of Druid, we started with a relational database that didn't work. We went to a like fully pre-computed H-based style schema that didn't work. And then we were looking at, okay, what are we doing next? And I worked at LinkedIn for a while with a guy named John Wang, who wrote SenseiDB. And it's a real-time search infrastructure that was open sourced out of LinkedIn. And I was talking with him about stuff because I was looking at kind of our dashboard and our problem. And I was like, you know, this looks kind of like search faceting. And it looks really similar to search, like what we're doing. And I was talking with him about like how things work. And I was like, you know, that infrastructure sounds like exactly what we need. And so I did actually look into using some search infrastructure. But the thing that I found with it, and this could just be my complete ignorance that spawned this, but the thing that I found when I looked at it was that search is built up around, like specifically faceting in general is built up around doing frequency counts. Meaning for this search query, under these terms, how many times did it appear for each of those? And then it facets based on a count. Where I needed to be able to do faceting based on actual aggregations, like give me the top of this value by average, or give me the top of this value by the uniques, by an approximated unique value. And when I was talking with John about putting that into the system, he was like, kind of doesn't work. You're going to have to take the value and concatenate it to the string value that you're returning in the facet, and then on the reading side, read it back out and spit it out. And basically from there, I kind of realized that search is built up around this idea of frequency counts and answering frequency count queries really fast, where I needed to be able to do top lists on actual aggregations. And that was actually enough of a difference to warrant a bit of a change in, to warrant actually implementing things differently. I could be completely wrong. I know that Solar and a lot of those people, they're doing a lot of stuff to do analytics and get at slicing and dicing and all that sort of stuff, but every time I've looked at it, I don't believe you can do a top list based on average. You have to do a top list based on one metric, a top list based on another, hope that the same values appear there, do the average, and then resort, and yeah.
I don't know how they do it, but Splunk has what you're saying. So it's interesting to see.
Okay. Right. I if you have Splunk's code, I would love to look at it.
Yeah, that's a good question. Yeah, so Spark is based on the MapReduce model, like the concept of mapping and reducing, but not on the MapReduce code base. So it can't just run arbitrary Hadoop jobs, although it is possible to convert your job to like manually, call your mapper and your reducer in it if you write a little wrapper program. In the case of Pig, we haven't done anything too special with it, although there is some interest in that. So maybe that's something that will happen in the future. We focus more on Hive at first. Yeah.
Other questions? Yeah.
So another question for Druid. As you were describing it, it sounded like a lot of things were similar between Druid and Cassandra. How would you, what are the main differences?
The storage model is very different. The Cassandra is kind of, at the end of the day, it's a key value storage model where you can have up to like 2 billion columns, and then people that use Cassandra override the fact that you can have so many columns into doing things like inverted indexes and things like that, where at the end of the day, the storage model for Cassandra in my mind is very similar to HBase. It just has some nice properties that allow you to do a little bit extra, where Druid's storage model is actually very close to a relational database, where it's actually not possible to say, give me this row. There's no ID associated with a specific row or specific document. It's just the thing is there and all of the queries let you scan on top of it. If you wanted to find a specific row, you would have to have some filter that filters down to exactly that row to pull the data out. And so it's kind of the biggest difference is in that storage model and how it goes.
I'll throw in a question. To get you out of your projects, oh, that'll be a good last question. I'll skip that just in case. How do you get buy-in if there's a concept, an idea that you want to incorporate, but you're not the person who can do it, at least you don't maybe have the time to do it on your own? How do you manage? How do you build a team of people and get the sort of conviction to do something if there's no corporate structure?
So in the Storm project, I think we kind of logically just simply using this. I mean, there are two things for us. Right? One is the mailing list, and there was quite an active discussion over there. Then secondly is this GitHub things like issues is that, and tended to have a lot of discussion over there. Then even you do not if the stuff you try to discuss got enough attention from the community, even if you do not have time to do it, tend to have some passionate guy in somewhere in the group will jump in, take on it.
I think it's a very good question, and I want to know the answer as well.
I think no one knows the great answer here. I mean, I guess there are two settings here. One is the open source community. I think in the open source community, the key part is to have a project that is successful in the sense of you deliver things that the users want. And when you have a project like that, the other users and contributors are aligned well with you. And I think all the projects here, for example, have that property, and you can move quickly, and you can, pass through architectural ideas and things like that. In terms of actually people you work with day to day at the same place, I don't know. It's very hard. You hire good people, but it's very hard. Yeah.
Talk about message passing. Oh. Okay. So let's thank the panelists.